Welcome back to the Deep Dive. Today we're plunging into the Mesozoic oceans to look at the Ichthyosauria, the fish lizards.
Right. These were incredibly dominant marine reptiles, truly masters of their domain for a very long time.
And the really striking thing, isn't it, is how much they look like modern dolphins or even tuna.
Exactly. It's perhaps the best example we have of convergent evolution. You've got these animals descended from land reptiles returning to the sea and independently evolving this perfect fish-like or dolphin-like body shape. Streamline, dorsal fin, powerful tail fluke. It's remarkable.
And this wasn't a short experiment. Their timeline is vast.
Oh, absolutely. They show up in the early Triassic, maybe 250 million years ago.
Wow.
And they persist all the way through until the late Cretaceous. About 90 million years ago, that's what, 160 million years of success?
That longevity really speaks volumes. And they weren't all small, were they? I read about some recent finds.
That's right. We have evidence on these jawbone fragments found fairly recently, 2018, 2020, I think, suggesting some species reached truly colossal sizes, maybe up to 26 meters.
26 meters.
Yeah,
That's the length of a city bus.
Pretty much. Imagine that swimming past you.
Hard to fathom. And the story of how we even first learned about them is fascinating, too, involving Mary Anning.
Ah, yes, Lyme Regis, early 19th century. Her brother Joseph found the first complete skull in 1811, but it was Mary who found the torso a year later.
The famous fossil hunter.
Indeed. And those finds eventually led to the whole order, Ichthyosauria, being formally named in 1835.
But the story didn't end there. Later finds were maybe even more revealing.
Definitely. Those German discoveries, especially from Holzmaden, they were exceptional.
Why is that?
Because they preserved soft tissue, finely preserved imprints. That's how we confirm they had these rigid dorsal fins and the big crescent-shaped tails. It showed just how hydrodynamically perfect they were.
Which brings us to their biology. Reptiles, yes, but breathing air and warm-blooded. That seems counterintuitive.
It does, doesn't it? But the evidence, particularly from isotope analysis of their teeth, is quite strong.
So they could generate their own body heat.
Yes, homeothermic endotherms. They maintained a stable, high internal body temperature. Estimates put it around 35 to 39 degrees Celsius.
It's significantly warmer than the surrounding water.
Oh, 20 degrees warmer, yeah. And we even have fossil evidence pointing towards a layer of blubber, like you see in whales, for insulation. Very mammal-like metabolism, really.
Which must have helped with deep diving. And their eyes.
Yeah.
They're famous for their eyes, right?
Oh, absolutely enormous. The largest eyes known for any vertebrate ever.
What does that tell us?
It screams deep diving, hunting in low light conditions. Calculations for species like Temnodontosaurus with eyes maybe 25 centimeters across suggest they could likely see or at least detect movement down to maybe 1,600 meters.
Incredible depths. True abyssal predators.
Exactly.
And their reproduction was also adapted for the ocean, giving live birth.
Yes, viviparous, born live young at sea. But there's an interesting detail in the fossil record.
What's that?
Well, very early forms, like Chahusaurus, seem to have been born headfirst.
Okay.
But later, more derived ichthyosaurs show evidence of tail-first birth, like modern whales and dolphins.
Why a switch?
It's likely an adaptation to reduce the risk of drowning during birth, giving the newborn a chance to surface for its first breath immediately. Another convergence.
So you have these highly specialized, warm-blooded, deep-diving, live-bearing reptiles ruling the oceans for millions of years. And then they just disappear, quite abruptly.
Yeah, it seems that way. Around 90 million years ago, near the Cenomanian-Turonian boundary event, it wasn't a gradual decline.
What happened? Not the dinosaur asteroid, right? That was later.
Much later.
Yeah.
No, this seems tied to a period of major environmental instability, rapid climate change, shifts in ocean chemistry and sea levels.
So climate upheaval.
Exactly. It seems this volatility wiped out key parts of the marine food web, multiple feeding guilds, and the ichthyosaurs, despite their adaptations, couldn't cope.
And it's important to note, this was before the giant mosasaurs really took over, correct?
That's a key point, yes. The timing shows ichthyosaurs were already gone, or very nearly gone, before mosasaurs rose to become the dominant large marine predators. So it wasn't direct competition that did them in. The niche was likely emptied by environmental change first.
So the final thought for you listening is this. Consider an animal that evolves incredible adaptations. Massive eyes for the dark, generating its own heat like a mammal, ruling the oceans for 160 million years. And yet, a relatively sudden shift in the global climate can erase it completely. What does that tell us about the power of environmental change and perhaps the limits of even the most successful specialization?